Hello, welcome to another Midnight Maths video. In this one, we're going to look at how we can find areas with calculus. And in order to do that, we're going to take a quick detour and look at how we find distances on the coordinate plane. So, for example, suppose we've got a y-axis measuring height of some mountain, and you're starting at 500 feet, and you want to climb to the summit, which is 1,000 feet above sea level. Now, how high do you have to climb? That's right, 500 feet. It's 1,000 minus 500, right? And so what we really did here was we took the y-coordinate of the top point, which we wanted to find distance, and then we subtracted the y bottom. So here y top was 1,000, and then we subtracted y bottom, which was 500. Now, why is top before the bottom? Because higher points will have a higher y value, right? And at the end of the day, we want a positive distance. That's why we didn't do, for example, 500 minus 1,000. Now, we can apply a very similar logic to horizontal distances. So, for example, say we have this x-axis, maybe it represents some kind of track. So we have 0 meters along the track, and then 25 meters and 50 meters along some kind of track segment. So if we run from point A to point B here, how far have we run? We've run 25 meters. And once again, we employ a similar technique where we take the x-coordinate of the right point, which is 50, minus the x-coordinate of the left. And because of the way that the x-axis is set up, increasing in the rightward direction, x right is always going to be more than x left, and so we'll get a positive distance value. So now let's look at areas, and we'll also see how this distance discussion comes into play. So here we've got an axis, and now we'll draw some functions here. So this green function, let's call it f of x. And let's call this blue one g of x. So now, how can we find the area bounded by these two functions? This shaded area here. Well, the calculus way to do it would be to take some rectangles. Suppose we take these rectangles right here. And we find the area of this one small little piece. Maybe we'll call this little piece some dA, right? So we find the area of this dA, and then afterward we sum up with all the other little dAs that are in this region. So the width of this small rectangle is going to be dx because it's a small change in the x direction. We're going to sum up all these rectangles. You know, you can kind of think of the integration as moving to the right, summing up the rectangles as we go. And what's the height of this rectangle? Well, as the rectangle gets very, very small, the height is going to approach the vertical distance between these two functions. Now, the vertical distance, just like we figured out with points, because functions are just sets of points, right? So we can use the same formula that we have over here to figure out vertical distances. So this one applies to vertical distances. So we have the y coordinates of every x value, right? That's what y equals g of x means. At this x value, we're going to have a y coordinate. So at any x value, the vertical distance is going to be g of x, which is the top function, minus f of x, which is the bottom function. So this distance will change as we move along the region. So we write mathematically dA is g of x minus f of x dx. Let's make this dA a little bit neater. And now all that's left to do is to integrate across the entire shape. So we will get that the total area of the shape is this integral right here. And we also need to put bounds on this integral. So let's suppose that this is point A and this is point B. Then the bounds would be from A to B. Because we're going in the x direction, so these need to be x values to match with the variable of integration. Now there is another perfectly valid way to find the area, because we didn't have to split up the rectangles like that. Instead, could have used this kind of rectangle. Still the dA, right? Because we're going to have to integrate eventually. And this time we're going to have to integrate sort of vertically, moving upward and collecting all the little rectangles as we go. And the width will be a dy this time because it's a small change in the y direction. But the length is going to be the horizontal distance between these two functions. And this right here applies to the horizontal distances. Now, we cannot say this is f of x minus g of x. Why is that? Well, f of x gives us the y coordinate of every point on this function, right? That's what y equals f of x means. But we don't want the y coordinate. We want the x coordinate of every single point. So what we'd have to do is solve this. So for example, suppose this was just 2x. We would have to solve and get y over 2 equals x. And this would be your new function of x that you would actually use in the subtraction. So suppose you solved this and you got a different function, x. You got some x equals f of y. Now this is not the same f. I'm using the same letter. So we solve and we do the same thing for the other function. So we get x equals g of y. And again, these are not the same function necessarily. And now what we can do is we can find the horizontal distance, because now we're saying x equals f of y. This is going to give us the x coordinate of every point on the function, which is what we want, because we are dealing with horizontal distances. So here we put f of y minus g of y. So this right here, this f of y minus g of y, is going to be the horizontal distance of every rectangle. So we write it in a similar way we did last time, where we've got f of y minus g of y dy, and that's the area of a single area element, dA. Now we integrate, and we get the total area is equal to this integral. And just like last time, we do need to put bounds on here because it's a definite integral. And the bounds are going to be y coordinates instead of x coordinates because our variable of integration is the y. Now, I'll remove this a and this b, and in this case, we're looking at y is a to b. So these are really the two big ways to find areas of regions. One thing to notice is that the formulae only look a little different because of the way that I've named them. These are really just, after all, the top function minus the bottom function, in the case where we were doing vertical rectangles, or the right function minus the left function, in the case where we were doing horizontal rectangles. It's really important not to get caught up in all this formulae and really understand the geometric roots of where they're coming from. So that'll be it for this video. In future videos, we'll cover volumes and get into more concrete examples. Thank you for watching, and I'll see you in the next one.